Hello everyone, my name is Matt V. I'm this year's president of Imperial College Space Society, and I'm really excited to share with you our introduction meeting for October 2021. Tell you guys what we're all about and what we do. Hope you enjoy.
So I think there's one phrase to sum me up, and that is that I love space. I'm very passionate about it. And I guess so are you guys, because that's why you're here. We all love space for different reasons, and I'll start off with my point. On a personal note, for me, space engineering, space technology is really about personal motivation. Now, I want to wake up in the morning and I want to go to lectures and think about what I'm doing, but it has a kind of a larger meaning to it. I don't want to be, monkeys on a rock for the rest of humanity's history. I want to become a spacefaring civilization, and I want to contribute to that in some way. Blanca, do you want to talk about what motivates you?
Hi, I'm Blanca. I'm part of the Space Society committee, and I will be joining the CubeSat project this year. So personally, my motivation for joining the society was how much I love and I'm interested in physics, space, and exploration. I've always been really interested in it, and it's mainly because it's not just about obtaining scientific facts, but knowing space places us in the larger context of the universe. So I've always really loved it. So if you feel like me, you're in the right place. But even if you don't, and it's not your main field of interest, it's a really great opportunity to work in such interesting projects and develop your skills with other students. So welcome. I hope you enjoy the presentation.
So whether you want to save the world through some Earth observation, or you just want to gather more knowledge, or you just like sending up rockets because they burn hot, you're in the right place, because this is what we're about, enthusiasm. But what do we actually get up to? We get up to 4 different projects. We'll talk about that later. We also have talks from industry leaders and scientists. We do organize hackathons for you to sharpen your skills and win prizes. And we also used to, at least, organize trips and quizzes. Understandably, over the past 2 years, we haven't done that so much, but we hope to revive that this year, God willing. And I want to reiterate this: whether you're a fresher or a PhD student, we want you to work with us. If you're completely new to engineering, completely new to space, or completely new to everything, it's fine, we'll teach you. And if you are very knowledgeable in your field and know a lot, we want you to help us and teach us. So no matter where you are in your career at Imperial, we want you. So let's talk about what happened last year. So on a positive note, we had lots of talks. My personal favorite was a talk from Blue Origin, or one of the employees. He described himself as a space architect. He talked about his career path, how he ended up working at Blue Origin, so his journey through architecture school into mechanical engineering, and then as an intern at NASA, and then Blue Origin, and then getting his final job as a distributed systems human habitat engineer. But he likes to call it a space architect. We also had talks from local space companies such as Surrey Satellites, Black Arrow Technologies, who are a rocketry company, High Impulse, and the research group CONEX, which are a student-led research group that created a really good and interesting concept about how to explore Neptune using legacy space equipment. Next slide, please. We also organized a hackathon last year. So this is a personal project of mine and Adam over here. We organized Making for the Moon, which was a totally online hackathon. We were sponsored by Spacebit, a London-based startup that makes really cool rovers, and BAE Systems, which I'm sure a lot of you know. The whole purpose of the hackathon was to allow students to tackle real-life space problems, and the problem was to lower a rover onto the moon with as little mass as possible and as cheaply as possible. The winning team of this, in fact, was from Imperial, because we also collaborated with teams from Oxford, Cambridge, UCL, TU Munich, and even some Australian universities. But yeah, the winning team ended up being from Imperial, and they ended up getting a work placement with Spacebit. So we really succeeded in our kind of goal of connecting you students of Imperial with the space industry there. This year, we're also organizing a hackathon called Leo Hack, also with Adam here. Can't share too many details about this right now because it's kind of top secret, but we're doing this with Robotics Society, so that might give you some clues. And we've already got 2 main sponsors, MagDrive and Lunasa, who are 2 kind of industry-leading UK startups for low Earth orbit servicing. Now, onto our projects. You might have seen these around campus. These are 4 posters. Some of them are legacy, so we've had them for years. Some of them are completely new. Some of them will be starting a completely new trajectory this year. Some of them will be building on from past knowledge. So the 4 projects are CubeSat, rocket engine design, high-powered rocketry, and space electronics. I'll now hand over to Philip, who's the leader of the CubeSat project, and he'll talk to you about everything that he does.
Right. Thanks, Matthew. Thanks, Matthew, for a great introduction. Hi, everyone. My name is Philip. Some of you already know me. So this year, I'm with my friend Peter, who should now shout from the heavens. Hi. Peter,
Hi.
hi. Again.
Hi.
This lovely fella. This year, we're running Project Daedalus. You might have seen our posters around the campus. And so you might, your first question might be like, what are we actually doing? So we have a quite ambitious goal of being the first civilian team to leave the solar system and go interstellar. And we want to do it at super low cost because we don't have much money. So that's why we want to utilize the energy from the sun and build a solar sail that will leave the solar system as quickly as we can. As quickly as we can means within 100 years from launch. So what do you define like as interstellar space? Heliopause, which is at 123 astronomical units. So this is our main goal. During this time, we also want to track the spacecraft. We also want to have it stable, passively stabilized. This is like more detailed goals. But now onto the system, what it actually involves. So the whole Daedalus systems contains of two main components, one of them being the sailcraft, which is exactly this thing. You might have seen the Freshersphere, which is the sail. And this thing will leave the solar system carrying a very precious payload on board, which is yet to be decided by ProBU. This payload will hopefully represent some human ingenuity, will have a cultural value. We're thinking of, for example, human brainwaves onto microchip or all of your names or something similar. Something cool we can actually send outside the solar system. Or even, stick in your hair onto this. So this will leave the solar system. But to actually get into space, we need a carrier probe, which will store it during the launch, keep it safe, keep it warm. And then while it's in space, it will unfold the sail, spin it up, so it's stable like a gyroscope, and then let it go because we don't need it. And also record deployment. So now the mission timeline. We won't plan to launch, of course, from Earth, but we want to use a very fancy thing called a piggyback mission because, of course, we need some delta V. How many of you have played Kerbal Space Program? Yeah, so you know how much delta V is important. And basically, you want to hop on an ESA or a commercial mission to Mars and gain some delta V from there. We don't want to go to Mars itself, but we just want to gain the speed. And after leaving Earth, we separate from the mothership, and we just go on our own. And the carrier probe then unfolds the sail, spins it up, and leaves it on its way. Then, how does it work actually? So if this is the sun, we are on a little bit elliptical orbit. Our sail starts to slowly accelerate on every pass, starts to slowly accelerate, as it finally reaches enough momentum to leave the solar system. And also, why is Saturn here, you might be wondering? Because I just wanted to mention we want to track our sail up to 10 astronomical units, which is roughly the distance of Saturn. Actually, I don't need to wear a mask right now. And after that, we sail off beyond our solar system and into the galaxy. Before that, we want to make a dress rehearsal on low Earth orbit. And for that, the mission will be very, very similar. As similar as we can make it. So we launch from Earth, we separate, we do the same things again. Spin it up, deploy, spin it up, detach, record. And on the LEO mission, which will hopefully happen within 2 or 3 years, we will test unfolding, stability, spin stability, as well as tracking, because we can actually use the infrastructure on Earth, such as GPS, to validate, cross-check how we're actually going to track it. And then eventually both of these spacecraft will deorbit. So onto the timeline. When was the project started, you might ask? The project was started way, way, way back in 2019 by Dr. Aaron No from the Aeronautics Department with his FYP student Esme. They did one concept study, and there was a first master's thesis and a first serious concept study done on the project. Then the project was left on its own for about 1.5 years. And during a chat with Dr. No in March, we decided to take it on and develop it from there. And so far, we had, from that point, 2 more master's theses written on the project. We've got first simulations of orbits, first lo-fi designs. And right now, we are here. And we've got today a new FYP student hired to the project as well. So the big new milestones that are ahead of us, basically in March, we want to have requirements, basically all the requirements for the mission. So you can start then the preliminary design review, which is PDR, which we will aim to have by June next year. Then we want to complete roughly the critical design review in the first half of 2022. For those of you who don't know, this basically we want to have a full project of every screw and cable on the system. Of course, we want to do prototyping beforehand, so we don't actually have to jump back every single time we do this. Then we want a low Earth orbit test between 2023 and 2024. And in 2026, we want to use the transfer window to go interstellar, actually go leave the Earth and go interstellar in roughly 2100. And yeah, fire some questions at us. This is my email and Peter's email, and I'll pass it over to Theo, who's reading the rocket engine design project. Thank you very much.
Let's see how painful this is for all of you if I use this as a lapel mic, and let's not bother with that. So hi, I'm Theo. I'm a final year mechanical engineering student, and I'm running Project Nuska, which is a terrible name in terms of clarity, but it's the name for the project that we're giving to the rocket engine design project. This is one of our long-running projects. We've been going long since I joined Imperial. I think it started in about 2010. That being said, we're not on our first engine. We developed about 5 or 6 hybrid rocket engines, and then we decided that we'd had enough. And we moved on to designing plasma thrusters. Then we decided that was too hard. And now we're going big on stuff we understand and going big with chemical. This is the kind of stuff that Jeff and Elon are getting hot and bothered over. So we are designing a chemical rocket engine to run on liquid oxygen and isopropyl alcohol, which is a rocket fuel that's not really been used since about 1941. So what we are looking to do for the rocket nerds among you is build a fuel-rich staged combustion cycle. If you don't know what that is, this relates to how a rocket engine hangs together, how it gets the power to pump its own propellants up to high enough pressure that we can combust them and throw them out the end to make propulsion. We're looking to go pretty high power at about 180 times atmospheric pressure in our combustion chamber and 251 times atmospheric pressure going into a turbine that we're going to have to design. If that sounds a bit ambitious, welcome to the project. We are looking to produce about 2.9 tons of thrust out of 10 kilograms per second of propellant. That sounds like a lot. The F1 engines that took the Saturn V up to the moon were using about 1,000 times more propellant per second. So we are on the big side of small, but the small side of big. In terms of the challenges that we're going to face during this is, first of all, design of all of these system elements, and especially dealing with extremely high temperatures. That 3,750 Kelvin is the temperature we're expecting along the center of our engine. That's pretty much higher than temperature of any material that we can afford to buy to build our engine out of. So if you're interested in looking at the challenges of designing rocket engines, so cooling down the chamber, chemical combustion, something we've done. If we go to the next slide, looking into the design of designing pumps and turbine blades to extract the power from our fuel so we can use it to pump our fuel to push our fuel out, which feels a bit counterintuitive, but I promise you it works. And if we go back a slide, cheers. This is the kind of thing that we expect it to look like in the end. This is the early prototype for the BE4 engine by Blue Origin. So this is slightly higher mass flow rate than ours, but a very similar fuel composition. So we expect to see an absolutely enormous blue plume caused by the richness of oxidizer in our exhaust stream. And we expect to see pretty patterns like that. And if that's not worth it, I don't know what is. I'm not operating on such a long timeline as Philippe for the CubeSat. I hope to produce explosions pretty quickly. What we're looking to do is we've started the project soon. We've moved on from our plasma rocketry this summer. And so this is a great time to get involved in the very early stages of designing a rocket engine from scratch. What we've done already is we've designed our chemical analysis, and we've figured out the majority of the fuel cycle in terms of power levels and kind of the approximate first order, I'm going technical again, the approximate power cycle and fuel rates. That's all good. We're looking very soon to have our turbo machinery manufactured. So that would be a good opportunity to basically produce a small jet turbine engine. that is going to produce somewhere around 200 horsepower of power, tautological. And we really hope that if all goes well, and if we get enough people on board and motivated to get involved, actually it's quite feasible that we could actually be testing a full-size rocket engine by the end of this year. We've got good access to machining facilities, and we've got a good amount of budget to work with. So let's go to space, or not. Well, let's build a rocket engine and find a field in Kent with a farmer who's willing to let us fire a rocket engine on it. So I'm Theo. That's my email address there that you mail. It's TJM. So just come and talk to me afterwards. I promise I don't bite that often. And yeah, that's Project Nuska. And if you want to find out why it's called Project Nuska, come and talk to me afterwards. Okay, I'm going to hand over to whoever wants it. Back love. Thanks a lot.
Hi guys, I'm Adam. I'm a fourth-year physics student, as you can tell by the bags under my eyes. I'm covering for Jakub today, who couldn't make it. He's the head of Project Rover. So next slide, please. Yeah, okay, so Project Rover is new this year. We used to be electronics. We used to make stuff like this. So for the past 2 years, we've developed our rocket flight computer. So this is something we designed from scratch at the end of 2018. We actually assembled it from scratch again, programmed it from low-level C programming, sort of, just changing files for operation of every single circuit in this PCB, up to high-level Python interfacing with GPS stuff, to do everything a flight rocket computer needs. So this PCB has everything in it that's needed for flight of a rocket. It collects telemetry data, it measures GPS positions, it transmits radio signals to communicate with ground station. And this year, we are hopefully going to improve its design and possibly expand on its capabilities, like increasing the flash capacity or the write rate to it, and optimizing radio communications, because we actually lost our only flight computer that flew because the radio on it was too weak. But mainly this year, we're going to focus on building a rover. So designing and building a rover from scratch. So the timeline is the electronics project was born in 2018. We built a flight computer. We launched it. We're hoping to improve it this year. But mainly, we're looking to start this new project where we actually design and build a rover. And what we do is dependent on you guys who join the project. So we can go in any direction. We can enter a competition and try and build a rover. We can just try and build a rover on our own, just build something unique. Everything depends on you. So yeah, if you have any questions, email Jakub or come talk to me. I'm going to be in the end there somewhere. Probably won't be able to answer all your questions because I'm not an expert on this project, but I'll try to answer as many as possible.
Hi, everyone. My name is Václav Pavlíček, and I'm second-year student of Electronic and Information Engineering, and I'll be leading high-powered rocketry project. And let's firstly try to talk about what the project is about, or who are the people who will be in the project. So we are students who are interested or in love with rockets since 2014, and we are applying theory that we were learned or that we were taught in lectures, and we are also, by applying this theory, we are gaining practical skills. And here you can see okay, and let's now talk about the aims of the project. So the main goal of the project for this year is to build a rocket that reaches a speed of 1 Mach, and also design its ground equipment and antenna for the Mach 1, and finally, at the end of the academic year, to launch it. And also, if you feel that this is too big for you, we've got some kind of beginner-friendly project, which is going to be participation in the National Rocketry project. And and it's going to involve building a rocket that is similar to one that you saw that just flew in the previous video. And now let's talk about the history of the project. So high-powered rocketry started under the Imperial College Space Society in 2014. And since then, we, for example, launched a Red Baron rocket. You can see a video of it. And in 2018, work on the project Mach 1 started. And first documentation and design files were made in 2019. However, there were some problems with legal requirements and also problems with COVID. So the work on the project was a bit postponed. But in 2022 and 2021, we participated in the national rocketry competition with our VK flight rocket, which you saw launching. Now let's talk about the schedule for this project. So firstly, I'll talk about national rocketry competition, which is like beginner friendly, or basically everyone can participate in this project, and it shouldn't be that hard. So in 2021, in November, we will form teams for this competition. We can have multiple teams per society. It really depends on the people who are interested. And in the beginning of 2022, we need to assemble the whole rocket. And by March 2022, we need to send the design report before we can launch the rocket. And in 2022, in June, we will hopefully launch as many rockets for the national rocketry competition as possible. And after that, we have to upload some launch reports with some data that we gathered from the launch. And now I'll talk briefly about the schedule for the project Mach 1. Firstly, I would like to summarize once again what the Mach 1 is going to be about. So we would like to build a rocket that reaches a speed of Mach 1. And it would be really nice if we could build a two-stage rocket. However, there might be some legal problems that we would need to tackle, but we'll see. But I think we hopefully can make it. And we'll also design a ground station and antenna with cooperation with the electronics team. And the proposed schedule for this project is to form team in 2021 in November. And firstly, we will go over documentation and designs that were already made. And hopefully, in the beginning of the 2022, we will perform our first communication tests with just the flight computer and the ground station. And then in the late spring and early summer 2022, the plan is to build and assemble the rocket and hopefully launch it in 2022, in June. Yeah, that's everything regarding the high-powered rocketry project. Feel free to drop me an email at vp92@ic.ac.uk, and thank you.
All right, I'm back. Nice to see you all, and thank you for coming.